Morning, everyone. Welcome to yet another fun week of environmental geosciences. Just a reminder, there is a worksheet that's up, went up yesterday. It's the last worksheet whose questions will be included on the second midterm, which again is going to be officially this Friday, but will be posted from 12:01 on Thursday morning, hopefully before all of you are up, or whether maybe some of you will still be up from Wednesday, and we'll be open until Saturday. So key reminders, the worksheet is posted, available, and it's the last questions that'll be fair game for the midterm. And the second reminder again is that the second midterm will occur officially on Friday, but you can take it from Thursday through Saturday effectively. For today will be the last lecture that'll be included, last lecture material will be included on the exam. And on Wednesday, I will post I'll do and then post a midterm 2 review for everybody to have and to study from in preparation for the midterm 2 as well. So all in all, again, don't expect too much different than the first midterm. Everyone did well, and I expect more of the same this time. So today we're going to talk about rivers and flooding. If those of you who, if you haven't seen any news or any discussion of flooding, maybe not yet this summer, but throughout the last few years, you probably haven't been paying any attention to the news at all. It's an issue that is quite pervasive, affects a lot of people, and does a lot of damage both to human life and to infrastructure on a daily basis. And what we're going to do, starting today and continuing later this week and into next week, is discussing some of the key aspects of rivers and flooding and getting the background into what actually goes into causing these occurrences. So some of the learning aims for today's, this week's lecture is just talk about the different types of rivers, how different cross sections or different shapes of the river channels will affect susceptibility to flooding or other types of hazards related to flood events. Talk about, in addition to flooding, how these profiles can impact sediment transport, erosion, and the factors of transportation of ships and other materials along those river channels. We're also going to talk, although it won't be today, about how land, or probably won't be today at least, but how land use change can lead to changes in river profile, frequency of floods. This is a major issue that affects society in a profound way. In addition to the sustainability aspects of population growth we talked about earlier in the semester, the way that increasing population is using land is changing quite dramatically. And in many cases, that can actually affect the likelihood for the frequency and degree of flooding to increase. And we're also going to talk a bit about different types of floods, the differentiation between things like flash floods, downstream floods, and sort of how these are monitored for and to the best of our ability avoided in modern society. The other component we're going to talk about is what we're doing about these factors of river channels and floods. One of the great debates that's occurred in society in the last few decades is the removal of dams, which of course can restore the river channels to their sort of previous existence, but also it's in and of itself can have profound changes on things like erosion patterns, biodiversity, and other aspects like that, as opposed to other parts of the world that are increasingly using new dams and using hydroelectric power and things like that to avoid greenhouse gas emissions. So there's a complex role of rivers, both in terms of flooding, in terms of hazards, and also in terms of their use for transportation and energy recovery. So we'll talk about that a bit as we go along during the lecture this week. The key thing, and I'll take some time on this today, the key thing that we need to, we'll talk about over the next series of lectures related to various aspects of water, is that rivers and streams, like groundwater and like the other factors we're going to get to later in the semester, are all integral parts of the hydrologic cycle. So this hopefully is a review for many of you. Many of you probably heard about certain parts of this. For other of you that have not, that's okay. But I'm going to try to introduce a sort of a big picture view of the hydrologic cycle. And basically what we're talking about there is how the global processes that control the cycling of water, in precipitation, surface groundwater runoff, and evaporation is driven. Ultimately, The key factor of the hydrologic cycle you have to consider is the sun. The sun is the component that provides the energy. That's solar radiation, in addition to driving things like photosynthesis and whatnot, is integral in the sense that it actually drives, most importantly, evaporation of water from various components of the Earth's surface. So obviously, given that 78% of the world's surface area, 75% north of 3/4 is covered by ocean water, the biggest source of evaporation in the surface of the Earth is actually going to be from the global oceans. Of course, those solar-driven radiation will cause evaporation of water at the surface of the ocean. So it's primarily from the top, just at the surface where there's a lot of sea spray and wave action that can cause evaporation to occur. The same process, of course, can occur in lakes. The Great Lakes themselves, everyone who's grew up near Cleveland or further north in Ohio is familiar with things like lake effect snow. And obviously solar radiation can cause evaporation from lakes just like it can from oceans. What some of you may have been less familiar with is actually the evaporation that occurs from surface run water. So basically, it could be runoff, it could be creeks, rivers, streams can also have some amount of evaporation. And the last two components that are maybe not known to some of you, but are a little bit more less straightforward to understand, is there actually can be evaporation from land. So the soil itself can have some water in the soil, which can evaporate by solar radiation and lead to cloud formation, just like the oceans, lakes, and rivers. And then the last one, which here is written as evaporation from vegetation, is something called evapotranspiration, or just transpiration, which is the fact that all the plants that live on the surface of the earth draw water into their roots. They use the water, and they actually exhaust the water vapor as well as oxygen from their stomata into the atmosphere as a waste product. So that amount of water usage can actually transfer a lot of water from the surface, typically soils, into the air directly. And all of those factors, again, are going to be major vectors for evaporation driven by solar radiation. So key components again here: oceans, lakes, rivers are obvious targets for evaporation. In addition to those particular bodies of water, the soil and plants make up major vectors for the transfer of water from the surface, or even subsurface in the case of plants, to the atmosphere by evaporation. Once the second component of that hydrologic cycle occurs, once that water actually gets into the atmosphere and nucleates clouds. So this process we won't go into in any great detail. We've talked about a little bit in terms of cloud formation and volcanic eruptions. But the key component here is that there's fine particles in the atmosphere called cloud, which are loosely lumped to being called cloud condensation nuclei. I won't test you on that, but those fine particles provide surface areas, and they allow that water vapor, as it eventually starts to basically rise, it cools. What's called the adiabatic cooling, or adiabatic lapse rates, about 6 to 9 degrees Celsius per kilometer that we talked about a few lectures ago. And on those fine particles, water can condense on the clouds and be suspended in the air, be transported around as the clouds you see seemingly every day in Ohio in the fall. Once those clouds form, they're going to be carried by wind patterns. So the same, westerlies in our region of the world moving from west to east, the trade winds, moving to the tropics, driving things east to west, are located in different locations, or blow in different locations of the Earth according to the Hadley convection cycle. But basically, the local wind patterns will drive the clouds that have formed, basically over bodies of water or away from the sources of land-based evaporation, and will drive those clouds onto, or over other parts of the world. And one of two factors will occur, but either the water saturation exceeds the saturation point for those particles in the sky. The cloud gets too much water vapor that it can actually hold together in this suspension of fine particles. In that case, precipitation will occur one from another. Or by and large, most of the precipitation is driven by the fact that the cloud actually continues to rise based upon the fact that it'll have a lower pressure, lower density than surrounding water-free air, such that's made of nitrogen and oxygen. and or the fact that those winds have to go over major mountain belts. So the cloud rises because it's less dense, or because the wind patterns actually drive it up above land masses. Either one can lead to that adiabatic cooling that we talked about. The cloud will cool, cold air can hold less water, and precipitation events as rain, snow, sleet, hail will basically occur. So sort of independent of the type of precipitation, we'll sort of skip over that for the time being. That precipitation can, of course, occur over bodies of water or on land. Particularly, we're interested as human beings in the type of precipitation that occurs on some forms of land, since that's where we live. And, you know, independent of the type of precipitation, the eventual fate of that water is to hit the surface and either flow as either called surface runoff or overland flow, where it can kind of percolate over the land surface, can get into things like creeks and streams and eventually rivers, and can run off into oceans or lakes. Or the alternative is, of course, that water can infiltrate into the soils and eventually into the rocks on the subsurface and become what we call groundwater. Now, that's not the end of the hydrologic cycle by any means. Of course, the water that gets into a lake, a stream, a river, or into the ocean can kind of be recycled again and again and again. And that's a pretty frequent process, of course, on the earth, on the surface of the earth. But even the water that gets infiltrated into the ground as groundwater can actually be cycled pretty quickly. Relatively speaking, on geological timescales, most of it is cycled pretty quickly through the Earth's subsurface. So, once the water infiltrates into the subsurface, there's a lot of pathways that can kind of be generated there. Water can be used by plants for sustain life, and it can release back to the atmosphere by evapotranspiration. It can be used for plant growth, obviously, or it can be pumped by humans for consumption. But if not, most of it will slowly flow down gradients, and the vast majority of the water will eventually discharge to a stream or a creek and be carried into the surface water and discharged back to the ocean. Some other factors, of course, here, things that fall as snow can be temporarily stored as ice or semi-permanently over hundreds or even thousands of years, can be stored in glaciers or ice pack, and then sometimes remelted and introduced into the subsurface as infiltration as groundwater. So most of the groundwater discussion will actually come about 2 weeks from now. So I'll skip over that for now. We'll come back to groundwater a little bit later. But for now and next week, what we're going to focus on more is the water that's incorporated as surface runoff into the rivers and streams, and talk about their role in terms of hazards and flooding. So don't forget the hydrologic cycle. We'll come back to it at least for the next 3 weeks. It's a major factor in thinking about sustainability and in day-to-day human survival. And it's an area of work that I work in a lot, that we'll talk about some recent things related to that in the last few years. So just an introduction now to the actual types of rivers. There's two main types of rivers. They're called bedrock and alluvial rivers. And bedrock rivers they don't all look as dramatic and beautiful as this, but they are commonly exposed in the bed and banks of, so the key here is that rocks are commonly exposed in the bed and the banks of the rivers themselves, of bedrock rivers. So if you look around in Ohio, a lot of the rivers, particularly northeastern Ohio and southwestern Ohio, are very easy to discern as bedrock rivers. You can walk up to them. You can see cobbles of rocks and rocks on the sides of the river channels, and basically the water is flowing over. And this more importantly, what we call bedrock is the rock in the bottom of the river is called bedrock, and these rivers are typically found in steep mountain areas and in areas of active, where you're actively eroding old mountain belts. So even though some of Ohio's central rivers and streams can look very alluvial, which we'll talk about that and what that is in a few moments, the fact that the Appalachians were to the east of us here, where there are major mountain belts kind of running northeast to southwest, so the southeastern half of Ohio is an area you're still eroding the Appalachian Mountains, and as a result, most of the river channels are actually would fall as or be characterized as bedrock rivers. So there's intact rock at the base of the river channel. The alternative, and this is again a end member type example, is the alluvial river. You'll notice that compared to this, where you see a large change in elevation over a relatively short period of time, not all as dramatic as this, and bedrock, here you're seeing a very flat-lying area across not just this river channel, but the area more broadly. And you'll note that there's almost no elevation change near the banks of the river here. So very flat-lying, and you'll notice also no rapids, no disturbed water, all very calmly moving through the river channel. So the key thing with the alluvial rivers is it contains the beds and banks are formed from soft, non-lithified or incompetent sediments. These are actually often sediments carried by the river itself. They get deposited in the bed of the river channel or on the banks. And often this will range from very fine grains, very small grains called silt, all the way up to maybe something that's only about the size of sand. But they're, at any rate, they are going to be, tend to be low energy. That means that the rivers are moving slow enough they can only carry relatively small particles, and in fact, are largely made of really fine-grained materials. Historically, this fine-grained material, as an example, has been mined for doing things, or not really mined, just recovered for doing things like making bricks and stuff like that. The really fine-grained materials you see in bricks and building materials, cement. So more generally, these alluvial rivers are commonly found in non-mountainous regions and in plains. So if you think northwestern Ohio, we don't really have any classic alluvial rivers in Ohio, but we certainly have certain creeks and streams that accumulate really fine-grained alluvium. More commonly, the alluvial rivers are in sort of coastal plains before you get to the ocean. So after discussing those two sort of river end members, and I should want to take a step back here and just say that there is, in many instances, stretches of even bedrock rivers where water flow is relatively, elevation is not very, doesn't change very much, where water flow can be relatively slow, and there's some alluvium that can build up, but by and large, we actually were able to go out to the field this semester and look around. You can see very easily the difference between alluvial and bedrock rivers. And you'll probably, as you start traveling again, either now or if you're traveling now or after COVID, you'll forever be able to see the difference when you get to most rivers pretty easily. Some key terminology here. This is just a generalized drawing of a river channel. It's neither designed to be a bedrock or alluvial river. But you'll see here that the area where water is actively flowing is actually determined, or is actually termed the river channel. You'll notice that the floodplain deposits are when the river floods on occasion. Sediments are deposited by the flood event, and you can often see these very clearly by looking at either direct evidence of deposits on the surface of the land surface near these river channels, or by looking at changes in vegetation. Often you'll see trees, and all of a sudden you get an area of really flat, low-lying, marshy grasses and marginal shrubbery, and that's often the way you can pretty easily map floodplain deposits. But basically, the floodplain deposits are this area of surface near a river that have sediments from rivers during flood events deposited on top of it. The name sort of describes it, I suppose. And then the floodplain extends on, the floodplain deposits, of course, are on both sides of the river. The floodplain is just the region around the river that is affected by flooding, and as a result is the maximum range of the rivers. If you're buying a house or you're doing risk assessments for people who are buying houses or building, schools or hospitals or housing or something like that, often there are pretty well-established floodplain maps by the FEMA. Even the USGS has some. There's been a lot of controversy in this in the last decade or so. They typically have something like floodplain, like designated floodplain. That means there's a flood event in a certain period of time, usually 10 years. And then they have 100-year floodplains where it's a greater, less risky to be in them. And then they have areas not designated floodplains. But the controversy in the last few years, and I'll post this on the website later today, is that as people have actually, over the last few decades, which people suspect is related to climate change, have actually reported where floods are occurring, there of course is an increasing frequency for people identifying floods on a 5, 10, 20-year cycle in areas that were previously designated as 100-year floodplains. So most people suggest this is direct evidence of climate change, but the point being that likely does include climate change, land use change, and also changes to the river channels we'll talk about later today, that have actually made flooding events occur more frequently and often to greater extents than previously suspected. So if you're getting to the age here in a few years where you're going to be thinking of buying a house, just be wary of the floodplains and be informed about just how reliable the 10 and 100-year estimates for floodplains are today. The types of river channels are often quite important to society in terms of how they've been used historically. If you look at some of the major cities in the United States, use this example in the Atlantic coast of something called the fall line. So the fall line is the boundary. It's a term derived from the eastern United States. It's the boundary between the alluvial and bedrock aquifers. So if you look here, map of the eastern seaboard, you go from Wilmington, Delaware, right through Washington, D.C., Richmond, Durham, Raleigh, right down through Columbia, South Carolina, Columbus, Georgia. And these are cities that fall almost exactly along the fall line. And that's not by accident. Historically, this is the boundary between two different, what are called geographic provenances, the Piedmont and the coastal plain. So the coastal plain is sort of exactly like it sounds. It's the area of the margin of the seaboard where you're getting close to the coast. It tends to be really flat lying, has a lot of almost all alluvial aquifers and a lot of things like sand and silt deposition in its soils. So tend to be flat lying, tend to be covered almost entirely with floodplain deposits. No topography or sort of bedrock geology to think of. As a result, in general, it tends to be, incidentally, not related to the discussion of rivers, tends to be relatively poor quality soil for agriculture as well. Inland from the fall line is actually areas where you see bedrock rivers with cobbles and rocks in the actual bedrock or in the river channel, and these areas tend to have some topography, so much faster moving water, often pretty useful for transporting goods, using hydroelectric power, things like that. So the point is, it's pretty difficult to move goods past rapids. So you can locally move pretty well along areas inland from the fall line, but over expansive areas, transportation is extremely difficult by river. So there oftentimes there's in the olden days, so to speak, moving 2 centuries back, there'll be a logging camp. We'll put the logs in the river and have them flow down, have people move them to the next area of them transport. But you really can't bring ships and things like that in. Whereas most of these areas here to the east of this are often really good port cities where people can actually come back up the alluvial river channels. They're pretty slow moving, they're not great for transporting things short distances, but they're really great for bringing barges and ships inland and actually having inland ports to basically transfer goods and stuff like that from outside the U.S. Excuse me here. One thing I was going to mention is that you can see this fall line very clearly in this topographic map. These are areas where the multiple successive mountain building events that led to the formation of the accretion of our continent we talked about very early on in the semester actually sort of happen here. You see mountain building, rifting, mountain building, rifting, mountain building, rifting several times. It's called the tectonic, Akkadian, and Alleghanian erases, which I won't test you on, but as a result, it's a very complex mixture of, or complex succession of rocks in this area that leads to changes in topography and, can have rapids and things like that that aren't good for long distance transport. So more broadly speaking, there's some terminology here that's useful to think about. This kind of looks at the ocean, the coastal plain, and with the fall line falling in here, and then the mountainous region. So that would be like a transect from here to here, as an example. And what you can see here is there's a couple of words I want to introduce here as well. Is that the actual this is a cross section here across the river channel. You notice that there the river valley tends to be V-shaped. Okay, it tends to be V-shaped because it's actively a river cutting down through the bedrock. And this isn't just water flowing down, cutting down through exclusively. You have to remember here that the mountain building events that occurred in the past in these regions have actually put a lot of crustal loading on the rocks in this area. And as a result, as the rocks erode, you actually see what's called uplift related to isostatic rebounds, where the stuff that got pushed down deeply wants to kind of re-equilibrate. And as a result, that river V shape comes from the water both cutting down and the actual rock moving up with the river cutting through it. The analogy I've heard is that when you think about rivers in these V-shaped channels in the mountain regions or bedrock aquifers, you have to think of them not just as think of it as a birthday cake without somebody just cutting the cake down. Sometimes they're bringing the cake up to the knife, or really it's a combination of the two really that lead to these V-shaped river channels. But notice as you actually look down, go downstream into the coastal plain, that same river, this looks at the Fox River specifically, the same river will have a very flat, narrow river channel and very broad floodplain. Notice here, there's a river valley, but there's not really any evidence of a floodplain per se. There can be, as we'll talk about here in a few minutes, or on Wednesday, there can be pretty disastrous flash floods in these sort of steep channel valleys, but in reality, you don't often see big, massive flood plains because it's taken a catastrophic amount of water to overflow the banks in these areas. Whereas the alluvial channels, particularly in the example of the coastal plain, the alluvial rivers rather, the channel can often easily overflow and expand out into these floodplains. And of course, once that's most rivers are relatively flat, slow moving, and depositing a lot of sediments near deltas once they reach the ocean basin. So importantly here, one thing I want to call your attention to is that notice that this entire area, which includes both alluvial and bedrock rivers, is encompassed by one delta environment. Basically, this drainage basin is the area that takes all the water from a region and brings it out to one discharge zone. Actually, it covers both coastal and mountain coastal and mountain areas, meaning it encompasses both alluvial and bedrock rivers. So often it's the same river can actually have different properties in different areas as well. So again, key thing here is the region drained by a single river or river system is called a drainage basin. And we'll talk about drainage basins here in a second. So the key thing as well as water is that where the drainage basin is basically bringing all the water out of that region, all the sediments that are eroded in that region and brought to the rivers are also moved along these river channels. And if the sediments aren't deposited in the river channels themselves, for example, in floodplain deposits or in alluvium in the alluvial bed, the water and the sediments are actually discharged to the ocean in those same areas. And that goes back to the discussion we had last week about prograding deltas in areas like the Gulf of Mexico, for example. Obviously, if the sediments are starved, we'll talk about that, how that could occur in a bit more detail later. We can prevent that like you're seeing in New Orleans today. So this is one of my favorite maps of the US. It's kind of, in my mind, quite provocative to think about. Notice we're here in Ohio. Most of Ohio is actually part of this big pink drainage basin. And you'll note that into the Ohio River, and then, whether it's via the Scioto or the Olentangy into the Ohio, will eventually make its way down and drain out of the Mississippi River. So most of the surface area of the United States is actually drained by the Mississippi River. That means both the water and the sediments, of course, are drained in that region. But notice that there are also many other drainage basins throughout the United States, some of which drain into the Great Lakes, or many of which drain in the Great Lakes, a lot of which locally drain to the coastlines. So notice that there's sort of much smaller drainage basins in these individual river channels that get to the oceans, but inland, many of them sort of accumulate water in mass. And you probably have heard this before, but just for perspective, just remind you, that everything from the continental divide in the Rocky Mountains to the east, and everything from the continental divide in the Allegheny, or the Appalachian Mountains, to the west of the Appalachian Mountains, all will drain the Mississippi River in the vast majority. Some locally discharge the Great Lakes. Of course, some others that don't actually, they're internal basins that don't really drain out and just sort of accumulate. But generally, closer to the coastal areas, you'll notice that there are much smaller drainage basins. And this is actually, from the Colorado River, which I've talked about a lot towards the end of the semester, drains much of the Western Rockies, and this is all to the drains into the Willamette Valley or the Puget Sound here in the northwestern part of the U.S. So we'll come back to each of these a little bit later in the semester. So we introduced the idea of the sediment load is actually moved as well as the water in these areas. And we're going to talk a little bit about the sediments before we go further, just because it's a pretty important part of understanding the hazards and the implications of changing river channels and things like that. So the first term I'm introducing here is the total load, and that's the total quantity of sediment that's actually carried in a river. So that includes the bed load, the stuff that's sort of getting pushed along the bottom of the river channel, the suspended load. The suspended load are really particles that are small enough to be suspended in the river as it flows. They don't dissolve, they just sort of float along. They get carried by the flowing water itself. And then the dissolved load, and this is what's actually chemically dissolves into the water. And I'll talk about each of these here in more detail in a second. With the total load, again, is the total amount of all these things are moved by a given river. So the bed load, these can be boulders down to cobbles, and even relatively small grains, sort of sand-sized grains in many cases. And they move around the bottom of the river by sort of bouncing and rolling as they go. Often they can be broken down to smaller bits and break down pretty easily as a key component of mechanical and chemical erosion. And these tend to be, in most rivers, really small components of what the river produces. That kind of makes sense if you think about it, right? They are big, massive blocks of material in many cases, or small cobbles, even gravel. And even though they can make up a relatively important part of the mass, maybe up to including 10%, in most cases, they're much less than that, and they require relatively fast-moving rivers. I'm going to reintroduce the idea, or the concept here, of something called Stokes settling velocity. And what that basically, again, says is that the amount of mass of the particle, as well as the shape as a roller too, but the mass being most important, determines the amount of the rate at which water needs to be moving to keep the particle suspended. So obviously, a big particle boulder, doesn't really matter how fast the water is moving. It can be suspended for short periods of time. It can be bounced along the bottom, but it's really hard to imagine situations where big particles can be moved without incredibly rapid volumes of water. And in most cases, the water is moving too slow for the bed load to be more than bounced along the bottom here and there. What becomes important in that Stokes settling velocity, consideration is the suspended load. The grains from sand to silt are actually determined by the grain size, and silt and clay, even being smaller than sand by quite a lot, almost an order of magnitude smaller than sand in terms of size, can actually be carried. They're light enough. The Stokes settling velocity means that they don't really get they don't sort of drop down through the water column. They actually get suspended and carried with the water quite freely. As a result, for the suspended load, most of the material can be carried by the flowing water for great distances. If you look at the sediments, for example, the example I've given you in New Orleans and what's coming out from the Mississippi River there, in many cases, the particles are suspended for hundreds of miles, in many cases farther than that. That's sort of that muddy water as you see sort of slowly draining out of the Mississippi River. The suspended load is the key component of the total load in most rivers. Generally accounts for about 90% of the total load, and this again gives rise to that muddy or red or brown appearance in most of the rivers. Important thing to recognize here is that these particles are barely, if you bring this water out, put it into a jug, and watch it settle for a few hours, you can see this mass of particles in the bottom of the jar, if you will. But in reality, if you look at them individually, they're incredibly small. And, it's really that even though they're really small, it implies how much of it's there to make up 90% of the total load compared to these cobbles you can see rolling down river channels in the bed load. And then the last component, not trivial in terms of the biodiversity and biological processes, things like primary productivity that we talked about in the last class, is the dissolved load. So these are things that are dissolved in the chemical solution. These are derived from chemical weathering of rocks. So these can be things like acids reacting with carbonate rocks, putting things like bicarbonate ions or calcium into the surface waters. Another thing here is silicate minerals. We talked about very briefly at the beginning of the semester, and I won't test you on any detail, trust me. They actually can slow silicate weathering can release things like sodium, potassium, magnesium from silicate rocks, and all of these things can dissolve and say dissolved, and that, therefore sort of like the ultimate suspension. They're chemically dissolved. They stay in the solution for permanently, and actually are a pretty important component of delivering key nutrients out to the deltas and the end of river channels. So again, total load is all these components combined, the bed, suspended, and dissolved loads combined. Most of the materials in the suspended load, that's an important thing I want to highlight for the midterm 2. Bed load can be very big cobbles, but makes up a small percentage. And dissolved load can be really important, but actually makes up a sort of typically an infinitely small percentage, often less than 1% of the total load, although in an important bioavailable chemical form in many cases. And going back to the topic we brought up in the last week about nutrient pollution, nitrates in particular, they are often anthropogenically introduced to the total load, but they're actually delivered in a dissolved load, which is what makes them so difficult to remediate from reaching the global oceans. So for perspective here, this whole process of carrying sediment loads in these various rivers is a big mover of mass on planet Earth. 15 to 20 billion tons of sediment are transported via the global rivers into the world's oceans. The reality is every time we do more reliable surveys in polar regions such as the Arctic and Arctic, that number gets a bit bigger. We used to think that there wasn't much erosion happening there, but we know now there is, and it contributes. So if you remember back to John Hutton, who originally came up with the idea of the different stratigraphic layers and incorporating the amount of time, trying to get an estimate of the age of the Earth, actually, of course, he had the age of the Earth wrong by quite a bit, but he was cognizant of how much material was moving and how much time that would take to create all the landmass that we saw. So I just wanted to bring you back to the idea that, if these rates were sustained and there was no subduction process recycling these through the Earth's interior, you'd fill the global oceans up in, a few million years, which is actually how he used to originally get an age of the estimate of the Earth. But now, of course, we know subduction transport these things into the Earth's mantle and recycles them through the mantle and sort of restarts the process. I'll show you a series of pictures like this, but this is just an example on the east coast of Italy, of sediments draining into the Adriatic Sea, and you can see that there's major amounts of sediments all along this coastline. Does anyone want to take a guess as to what types of rivers are depositing this in the material? Does anyone want to guess bedrock or alluvial rivers that are bringing this massive amounts of fine-grained sediment into the Adriatic Sea? So no guesses. So oh, we have some guesses. So we got bedrock and alluvial. So I guess that based upon that response, I'm guessing that you sort of got a little bit of the trick question. But actually, most of the erosion. So the answer is actually alluvial rivers are bringing this material into the Adriatic Sea. But it's a combination question, much like the fall line that we talked about with the east coast of North America, or the east coast of the United States in specific. Is that this is the Apennine Mountains. It's a massive area of relief, and most of the area from here to the coastal plain comes down as bedrock rivers that actually are pretty rapidly eroding, and you often see large bed loads and large amounts of relatively large particles, a large volume of relatively large particles that are being deposited in these rivers and bedrocks. And you actually can see here, not incredibly well, but you can see it, a fall line right along this margin here. And hopefully you can notice that there is a a change. I should have drawn that rather than just put the arrow there, but you can see a change to this dark green vegetation. So this is in the montane regions of the Apennines, often very heavily woody trees. And then as you come down across what would be called the fall line in eastern Italy, you notice the color of the vegetation changes. You see more grassy, low-lying vegetation, bushy, and you see flat-lying, relatively flat-lying coasts. So here you're still seeing that what's different about their alluvial rivers, of course, is the fact that our alluvial rivers, it's relatively flat-lying, and you see a lot of meandering of the rivers. Here, there's still enough water velocity from the Apennines that these have relatively more straightforward paths to the ocean, but these would be bedrock rivers until they get to the local coastal plain here, and then be alluvial rivers out into the Adriatic Sea. So it's a combination of both, but alluvial rivers are what's directly connecting to the Adriatic Sea in this location. So you can see here some examples of how this is sort of changed with time. Oops, excuse me. This is actually looking at the Sugata Bay in the Pacific Ocean, and notice here that with time, this is after a major rain event. You can see that the normally amount of alluvial rivers have sediments that are coming out and getting into the Sugata Bay, and this is actually after a major monsoon event in the mountain area. So notice you increase both the sediment load, and notice there's also a change in the coloration of that sediment load. It's not just an intensification; it's a combination of intensification and more of a bed load component, actually reaching the ocean. So it can be a complex mixture of both, and certainly the Adriatic, the base load, what's getting out there is largely silt and alluvium, but at major rain events, you can actually see both materials being deposited. In many cases, as we talked about, an example of New Orleans last week, there you can actually see permanent sediment deposits, alluvial fans or deltas deposited where these materials, the sediments, are carried by river channels to the coastal areas, and often that rivers flowing from mountains onto plains. And these can be relatively small creeks, actually, but it can be also, in this example, could be a relatively large river. So great range in size. They'll often, at the area where the elevation changes, where there's vegetation from woody to brushy change as well, you can also see major deposition of alluvial fans in those areas. And that's what you're seeing here, a pretty classy example. Notice they sort of a prismatic shape to them. If you're looking at it from the sky, it sort of has a prismatic shape that sort of fans out at its distal margin and comes back to a peak right exactly at the river channel, back to this proximal margin. And of course, these are common if you go out to the western part of the United States, even though it's a fairly arid region, in periods of intense, snow melts, stuff like that. You can often see alluvial fans getting deposited in certain areas, each year annually. So these alluvial fans can be really important in some regions for delivering nutrients, important for agriculture, and oftentimes you see, particularly in the western parts of the U.S., you see these are sort of utilized for where you would do farming, partly because it's the only non-bedrock component. It's where the fine grain materials there you can actually plow and till much more easily. And of course, the other example here is deltas like New Orleans, where you can see major deltas being formed into rivers, and where those rivers carry particularly where alluvial rivers carry fine grain materials into the ocean, or still bodies of water like large lakes, you can see major deposits of sediments that can lead to delta environments that can accumulate sediments over a long period of time. Again, I've said this last week, I want to stress the importance of it. The natural process is that newer sediments are coming down, and most sediments, most rivers sort of see a progradation as long as there's a sediment supply. Clearly, as we talked about the damage long-term from hurricanes, this can be, if you remove that sort of protective mechanism, this can be pretty disastrous land use change, where sediments are being not accumulating in those deltas, and as a result, you can see the deltas become sediment starved and start actually being lost. So I'm gonna talk about we move from sediments here. We're going to move into the discharge of water. But what I'm going to do instead of going on here, this is sort of a natural transition from sediments to water. I'm going to end here, which is the final part of the materials for the second midterm. We'll pick up with water discharge on Wednesday after the midterm review. So again, I'll start class on Wednesday with the midterm review. I'll move on to the lecture talking more about waters and getting back to river channels. But all the material to this point is where I'm going to end the period for the second midterm. So I'm going to stop there for today. Let you get out here. I saw a question about showing the last slide really quick. Is this the slide you're referring to? Okay, I'll leave here, but this is where we're going to end for the second exam. So review on Wednesday. Exam will be posted. Midterm will be posted on Thursday morning at 12:01. So basically Wednesday night, open until Saturday. If anyone has any questions, let me know. If not, I'll see you for the exam review on Wednesday. There will be no new lecture on Friday. I'm going to leave the Friday time period open if anyone wants to do the second midterm during that time. So there'll be no new lecture on Friday. All right, I'll stay on if anyone has any questions, but if not, I'm going to end there. Thank you all for participating.